think we're going to start. Those that are late will miss the most fun part. Are we good? Okay, so my name is Boris, and today I'd like to talk about modules, C++ modules, more specifically practical sides of them. There's this funny quote from the standard. Those of you interested can go read it in detail. But it summarizes well what the standard can and cannot say. So we're going to say a bit more. The plan is as follows. We are going to introduce modules as a language feature. Then we'll look how that affects the build system. Then we will try, with that understanding, we'll try to get some basic design guidelines for modules. As you will see, it's not as straightforward as it might seem initially. And we will close off with, again, some guidelines on how to convert existing code bases to modules, as well as provide backwards compatibility with headers if we need to. Okay, so let's just dive in. Lots of ground to cover. Why modules? First question. What are the benefits? Well, modules provide isolation from preprocessor macros as well as other module symbols. Modules also force us to explicitly export entities that should be visible to the module consumer. So in this sense, they are a physical design mechanism that forces us to think about how we structure our code. Modules are also a first step towards not needing the preprocessor, at least in most translation units, hopefully one day. The most commonly used preprocessor directive is include, so modules make it hopefully unnecessary in most cases. Modules also open the door for a reliable and generally available distributed C++ compilation. But modules, a build system, can make sure that the compiler on your local host and a remote machine have exactly the same set of inputs. This is not the case with headers. Compiler searches for headers on your machine in some unspecified directories, and it's hard to make it work reliably unless you have a tightly controlled environment. Did I miss anything? Right, this is what we are all here for, right? Who cares about that other stuff? We want faster build speed. But anyone knows how fast modules will make our builds? Anyone seen actual modularized build of a library? Well, there aren't many benchmarks. And the reason for that, we also state that clearly at the outset, is that modules are still a work in progress. While this might all seem smooth to you, there are a lot of rough edges, especially in the implementations. Also, I forgot to mention, we are talking about modules TS, the specification that is proposed for standardization. Some compilers provide their own flavor of modules, for example, Clang, so we're not talking about this today. All right, so how fast can modules make our builds? Well, we modularized a real library, so I'd like to show you a demo. This is a build-to utility library, so it's like a low-level library with some basic utilities that we use to build the rest of the tool chain. It's, I would say, probably small to medium size. It has a little bit over 30 modules, a bunch of unit tests. So on the left, I have a modularized build, and on the right, I have exactly the same source code, just built as headers. So I'm going to show it side by side because it's quite illuminating to see the difference in the build, in how the builds feel. I'm going to give each build 2 cores. This machine has 4 cores. I also disabled turbo boost, so we have a fairly even playing ground. Okay, so you have this little contraption with locks to make sure that they all start at the same time. Okay, ready? So left we have modularized build, right we have headers. Exactly the same end result. And to me, the header build feels a bit tedious. So here we get about 2.5 speed up. If we run it separately on all cores, we get about 3 times speed up over a header build. This is, by the way, with Clang, and we are also using Modularized standard library from GCC. Okay, so hopefully I have your attention now. What exactly is a module? Well, it's actually hard to answer this intuitively and shortly, so we're going to try to answer this question from 3 different perspectives: that of a module consumer, a module producer, and a build system that tries to make the two play nice. But let's make something clear at the outset: modules are a language level mechanism. They are not a preprocessor level mechanism. It's an import declaration. It's not an import directive. Okay. From the module consumer, a module is a collection of external names called module interface that become visible once the module is imported by a consumer. So to import a module, we use the import declaration, import keyword followed by the module name. Module name is a sequence of dot-separated identifiers. The standard does not prescribe currently any hierarchical semantics, though it is customary to refer to, for example, hello core as being a submodule of hello. We'll talk about what exactly that means in a bit. What exactly visible means? Let's quote the standard. An import declaration makes exported declarations visible to name lookup in the current translation unit in the same namespaces and contexts. Note, the entities are not redeclared. So this is quite a bit different compared to headers. When we include a header, we get a declaration. When you import a module, names are merely made visible. One intuitive way I like to think about it is, imagine you had a single giant translation unit where you copied all your modules and all their consumers in this one big, say, file. So in this single translation unit, nothing will be redeclared. You will only have one copy of everything. And everyone will see declarations in exactly the same way, in exactly the same namespaces and contexts. This visibility semantic suggests that modules are not a name scoping mechanism, right? Modules and namespaces are orthogonal concepts. Modules can export names from any number of namespaces, including global namespace. Namespace name and module name need not be related, though generally it makes sense to have a parallel structure. Discuss that in a bit. Specifically, an import does not imply any additional visibility or qualification for names declared in namespaces. So here's an example. Let's say we have a module, hello core, which exports function f in hello namespace. Merely importing this module does not mean that you can call f unqualified. So we still have to use the usual qualification mechanisms or a using directive. Modules also deal with names, not symbols. Everyone is clear what the distinction is. Well, a quick way to recap. Names are what compiler complains about, and symbols are what linker complains about. Right? So modules talk about names, not symbols, and we use the usual. If we are using a name from a module, we may have to satisfy its symbol in the usual way by linking an object file or a library. So in this sense, modules are pretty similar to headers. And like headers, they make perfect sense in programs, not only libraries. In fact, a library can have private or implementation-specific modules that are not meant to be used by module consumers. Okay, so that was the consumer perspective. Some new concepts, but I think fairly straightforward. The producer perspective, necessarily more complex. Before modules, we had a single translation unit. Now we have single type of translation unit. Now we have 3. We have the module interface unit, we have the module implementation unit, and we have the old kind, which we'll call a non-module translation unit. So from a producer perspective, a module is a collection of module translation units, exactly one interface unit, 0 more implementation units, and I must add, and this is unlike headers and makes a lot of people excited, A module interface unit can define non-inline functions and variables. So we'll see where that leads in a bit. A translation unit is a module interface unit if it contains an exporting module declaration. Right? Export module and then the module name. You can guess probably, and it's an implementation unit if it contains non-exporting module declaration. Now let me also note that this is a fairly new syntax. It's not supported by all compilers yet, notably Visual Studio, but I believe that's going to be the syntax going forward. All right, so I think you get an intuitive feel that module interface units correspond to headers, and like headers, it makes sense to distinguish them with a different file name extension. Well, the compiler vendors predictably suggest different extensions. None of them make much sense to me, honestly. So my recommendation would be, if you're following the HPP, CPP naming scheme, like Boost, for example, then the natural choice would be MPP. Another popular scheme is HXX, CXX, then use MXX. And if you're using something else, perhaps now is a good, when you're switching to modules, maybe it makes sense to also switch to one of these two naming schemes. A module declaration starts a module purview. Now, this is a fairly central concept in the module machinery. Names declared in the module purview belong to said module. Right? So, in a sense, a module declaration, exporting or not, either in the interface or an implementation unit, it splits the translation unit into two halves, which we will see have very different rules. So here, an example, we included std_string header out of the module purview. We then have exported module declaration, which starts the module purview, and then we declare a function which now belongs to this module. A name belonging to a module is invisible to module consumers unless explicitly exported. Right? So this is the explicit exportation semantics. And name can only be exported in the module interface unit and only in the module purview. And we can use several syntactic ways to do that. There are several syntactic ways. We can use the export specifier before any declaration, like here we have an enum class and a function. If we have a bunch of names that we want to export, we can use an exported group without too much repetition. Finally, we can also export a namespace body. Notice that it only applies to the immediate body. So in this example, this function is not exported unless we also stick export here. So far we've been talking about names. What about corresponding symbols? This is where it gets a little bit interesting. A module has this curious ownership model as specified currently, which is called the weak ownership model. So in this model, names that are exported, their corresponding symbols are unchanged. So they look exactly the same as if we actually never used modules. Those that are not exported, they have what is called module linkage. And names that have module linkage are only visible in this module purview. So they are essentially private to the module. And they cannot clash with identically named names in other modules. So to give you an example, let's say you have two modules, each of them declare non-exported function f in the global namespace. If you link those two modules together in a single program, everything will be fine because those symbols are private. So this is normally implemented by decorating module linkage symbols with the module name. This first point, the fact that an exported name looks exactly the same as if we declared it without any modules being used, has one very important implication. And that is, we can build a library as modules and consume it as headers, and even the other way around. We can have a library that was built with headers. If we can come up with suitable modules, module interface units, we can consume it as modules. And we'll see where that leads in a bit. What about the preprocessor? Modules do not export macros. Furthermore, a consumer of a module cannot affect the interface that he or she gonna get by defining any macros. So in this sense, the consumer and the module interface, they're isolated from each other when the preprocessor is concerned. That is not to say that either cannot use preprocessor. It's just the preprocessor stuff does not leak through the interface boundaries. One practical implication of that is that import or the order of importation is not significant. Names made visible. This is also an interesting point. Names made visible by an import declaration in the interface purview are automatically made visible in the module implementation purview. So here we're importing hello core, that exports say hello. We don't need to duplicate those imports in the implementation units. So in this sense, an implementation purview is kind of an extension of the module purview. And I think it's pretty nice that we don't have to repeat this stuff. So here we exported say hello. We don't need to do anything else. In the implementation unit, we can just call it. This is not the case, however, for consumers. So this is the same example, except now instead of an implementation unit, we have a consumer. So if we merely import hello core, hello extra, the say hello function that was imported from the hello core module is not automatically visible unless the interface decides to re-export the imported module. So this is this funny looking syntax. Caused quite a commotion on Reddit, but I think it actually makes perfect sense. So you export imported module hello core. Re-export is the mechanism for assembling modules, a bigger aggregate modules out of submodules. So here, for example, we have 3 small modules in our library, and we want to make it easier to import for the user. So we just create an aggregate module which exports the other 3. Pretty simple. Okay, so that is the producer perspective basics. Let's now take a look what happens in the build system space. The central piece of the module infrastructure in the build system area is the binary module interface file. It's produced by compiling the module interface translation unit, and it is required when we compile every translation unit that imports said module, as well as its implementation units. Let's see how it actually works by building a simple modularized program with the 3 most popular compilers. This is our simple interface, implementation unit, and a consumer. Right? Pretty straightforward, nothing. Single function, implement function, import module, call it. People ask me, what do I do? So I say, well, I write software, and they ask, what kind of software? I say, well, build systems. What is a build system? So these days, I just keep this on my phone, and when someone asks me, I just show them that, and there are no more questions. But it's not that bad. So let's start with GCC. Just to recap, we have 3 files: interface unit, implementation unit, and a consumer. The first thing we do, we compile the interface unit to produce the binary module interface, BMI. So here in GCC, it has the NMS extension for the time being, might still change. So here we use the option to specify where to put this binary module interface file. Notice something else. Besides the interface, the binary interface file, we also get an object file. And if you think about it, it makes sense. Remember I said that an interface unit can define non-inline functions and variables. So those have to go somewhere, right? So that's where they go. We have to link, as we will see in the last line, we have to actually link this object file to when we are building our program. So the next we build the interface implementation unit. The only difference compared to vanilla compilation is that we have to specify where to find the module. this implementation unit for? Well, the BMI for this module. The compiling of the consumer is exactly the same. In fact, the option is used exactly the same. So the reason we have to specify these two options in these two command lines. In the first case, it's because it's an implementation of this module. In the second case, it's because we are importing this module. Finally, we link everything together, remembering to also link the object file produced by when we build the BMI. Clang equivalent command lines. I'm not going to go into too much detail. The only difference here is that producing the BMI and the object file is actually a two-step process. We first get the BMI, which has the PCM extension, and then we compile that to produce the object file. But I was told that eventually there will be a mode to do it in a single compiler invocation. Visual Studio, again, pretty similar, follows the similar model to GCC in that we get both the object file and the BMI in the same compiler invocation. So it looks like, in a nutshell, supporting modules in a build system, an existing build system, boils down to two things. First of all, figure out in which order to build everything based on the import declarations. And then make sure that every compilation has access to the BMIs that it needs, to the modules that it imports. Well, the details are a little bit more complex, and to understand the implications of modules on our build process, let's take a look at a couple of build pipelines. So here we have time going from left to right. In each column, we list source files or translation units that we can build in parallel. Right? They don't depend on anything after that. So here's our plain header project. Everything is nice and simple. We have two translation units. We can compile them at the same time. Header is not listed because we are not building it. We are not compiling. So now we are adding a module. So now we have to compile the binary module interface first. And we cannot compile either of the other two translation units because they both need this BMI. Let's complicate our project a little bit. So we're going to add another module, which imports the core, the old module. We're also adding an aggregate module that re-exports the two. Then we have two implementation units, and we have a consumer that uses now the aggregate module. Pretty simple. So this is the pipeline. As you can see, it gets a little bit spread out and a little bit more interesting. I think most of you can understand why we have to build things in this order, right? We cannot build anything before we build the BMI for core, because everything else, recursively depends on it. In the second stage, we can start compiling extra, because it only depends on this, on the BMI for core, as well as core's implementation unit. Similar here, we have to start compiling. We can start compiling the interface BMI for hello, because it imports and re-exports these two, as well as the extra implementation. Finally, we can start compiling the consumer. Now, some of you might have noticed, especially looking at our first simple modularized project, is that it looks awfully like a generated header. Building a project with a generated header. Say we have a tool that produces our source code, for example, for serialization or database storage. And we first have to make sure this is generated up to date, and then we can compile our source code, right? So if we, for example, hello is generated by some tool, and it looks exactly the same as our modularized example. And so this might suggest that we can probably retrofit modules quite easily into existing build systems by just utilizing the same approach. Well, how do we handle generated source code in our build systems these days? Well, most of them, most popular ones, have some kind of a ad hoc pre-build step. Right? We first run some custom commands that make sure all the source code is generated, and then we have the main build loop where we build the graph and build dependencies in the correct order. Now, some of you might think, okay, well, we'll just use the same approach. This actually doesn't work very well. And the reason for that is that modules or BMIs are actually worse than generated headers. The problem with BMIs is that they depend on each other. So one module can import another, which means that you have to build things in the correct order. So you still have this discovery of the dependencies, creation of the graph, and building things in the correct order, right? Which you might as well integrate in your main build stage. A pre-build step will also greatly reduce your parallelism abilities, right? This is what a pre-build step will look for our slightly more complicated project. You know, if you have to compile all the BMIs before you can start compiling anything else, then you'll have this long drawn-out stage of, sometimes serial compilation followed by, when you can compile everything. So compare this to this. And of course, it's only going to get worse the more modules you get. What exactly is in a BMI? Well, it's compiler specific, but we can guess it can range anywhere from a sequence of preprocessed tokens to something close to the object file, right? And we all can also feel that probably the closer it is to the object file, the more benefit we are going to get, the faster our build will be. And this suggests that, in general, we should assume that BMIs are sensitive to compiler options we use to build them. This has a pretty nasty implication for build systems. Imagine you have a library build that you are trying to use in your program, but the two might be built with different options. And while the build system should strive to reuse BMIs for performance reasons, the options that we're using in our program and in the library can be sufficiently different that it has to actually build the BMIs for us on the side. So in build 2, we call it side build. So we have to build things on the side hidden from the consumer and use that. This dependence on compiler options or potential dependence, this is a very, and we also notice that this is a very murky area and unspecified currently. This dependence on the compiler options may suggest that BMIs are actually not a good distribution mechanism. Right? They probably should not be installed and should not be distributed. And instead, well, maybe with some exceptions like standard library provided by the compiler. And instead, we, for our own libraries, should probably install the interface unit source code, which, again, the build system has to be prepared to side build. All right, so that is the build system perspective. As you can see, some complications, but nothing, I would say nothing that we cannot handle if we have a proper build system, a proper mental model for our build system, no pre-build steps and so on. We also quickly mentioned the proposal for the standard libraries modules. Once you get modules in some workable stage, the next natural thing is to modularize standard library. This is still very early. Even the module names are not finalized. So yesterday I heard a complaint that there is no stud module that re-exports everything. And it's 5 lines of code. You can actually write it yourself. You don't even need a standard library permission. You can write it yourself, build it, and use it. So this is the least of our problems. So here's some basic modules. We have stud fundamental with basic utilities, stud core, which, by the way, re-exports fundamental and adds containers and strings. We have stud io for IO stream and so on, and we have stud threading with basic concurrency primitives. So I'm not going to go into too much detail because it's still very in flux. All right, so now we have a hopefully fairly good understanding of modules as a language feature, as well as some implications for the build systems. Let's see if we can derive some basic design guidelines from that. We'll start with module granularity. Now, how big should we make our modules? Well, and note that, well, standard says that importing a module should be, the cost of importing a module should be negligible. Unlike here, so this might tempt you to create what I call mega modules. That you just create one module for your library, right? Why not? It's free to import, easy to write. There is a big one negative implication for going this way, and that is recompilation. The bigger your module, the more likely it is that any single change that you make to this module does not semantically affect most of its consumers. But because it's a single module and you made a change to it, all of them will have to be recompiled. Right? This is, by the way, you might have noticed that standard library has quite chunky modules. Well, the standard library, this problem doesn't affect standard library because it doesn't change very often. The other drawback of mega modules is that if you have your interface littered with your implementation details, it becomes hard to read. You can work around that by moving your implementation details towards the bottom of the file, but you might as well just factor it into a separate translation unit. So the other extreme is mini modules, where you split everything into tiny bits and pieces, and this is both tedious to write, to maintain, as well as to import. So the guideline we came up with is to combine conceptually related and commonly used entities into modules. And this happens to also be a generally good design. Just to give you an example, let's say we are writing an XML parser, an XML library which provides parsing and serialization. It's fairly common for applications to only use one of these two functionalities, so it makes sense to provide two modules. We can also provide an aggregate module for ease of importation, though in this case, importing two modules instead of one is not a big difference, so I would personally not even bother. Okay, that question out of the way, how should we split our modules? Remember, a module module interface unit can have definition of non-inline function or variable, unlike header. So some of you might feel that this is a great opportunity to get rid of this whole header source file divide and be like Java. Well, there are a couple of drawbacks to going this way as well, and the main one is recompilation. Again, if you keep your implementation inside your module and you change this implementation, all the consumers of your module are going to get recompiled unnecessarily because they only need the interface. Right? So the guideline here is to have a separate module interface unit, except perhaps for simple implementations that are mostly inline or template. Like the inline and template function definitions and variables we still have to keep in our interfaces. But wait, what about header libraries? What happens to header libraries once we modularize things? Right? Do they become module-only libraries? Remember, now we can have the definition of a non-inline function in a module interface. Do we have the Holy Grail? Look at that. This will work. Well, or maybe we just got a better food gun. Right? The ODR rule is still in play. We still have to make sure that only a single definition of any non-inline function or variable ends up in the final program, in the final binary that we are building. Right? Also, what about incompatible versions? Let's say you have a library that is using a module, you might not even be aware, and you yourself is using some module-only module. Right? Interface-only module. You might have worked around its duplicate symbol issue, right? You, for example, threw away one of the object files, but what if the versions of the two are incompatible and you cannot use the object file from one in the other? Then finally, and this also applies to header-only libraries, where are the tests? So my personal belief or feeling or hope is that with modules, we will get better build systems and we won't need this crutch of header-only libraries or module-only libraries. Right? The only reason we have them is that they are popular and that everyone strives to make the library header-only is because they don't want to deal with build systems, right? Okay, so let's now look inside the module. So we kind of covered the meta topics, how big and how to partition. So now let's look inside. The first question that pops up is, where do I put includes? where do I put imports, which order I should do that. And there's actually a good reason why you should ask these questions. Remember, a module translation unit, either interface or implementation, it is split by the module declaration into two halves, essentially, right? We have the module Purview at the bottom, and we have outside of module Purview at the top. And the rules are quite a bit different. So out of the module Purview, we have the old rules. In the module Purview, we have the new rules, and specifically non-exported functions are invisible to anyone except the module itself. So with this understanding, who can tell me why this is a bad idea? Right. So what we did here is we included standard string in the module Purview, which means that all the names that it declared now belong to this module.
But it's not exported.
Yeah, but it belongs to the module. It's in the module Purview. So they become private names. And the end result of this can range anywhere from silent code blot to weird looking undefined symbols. Finally your std string in some kind of strange module for some reason is undefined. So the guideline is clear here. I think including headers in module Purview is a bad idea, except for some special headers. And the two common kinds are headers that only define macros, like for example configuration file or export file that defines symbol exporting macros, as well as headers that we actually want to end up in the module Purview. And a good example of that would be implementations of inline or template functions that have been factored into a separate header for code management reasons. Some of us like to do that. So here's an example. So we moved std string out of Purview. We then included export header, which presumably only defines macros. We can do it in Purview. Finally, we have to include the inline file at the bottom. It has to be in the module Purview. Okay, what about imports? Well, remember, import declaration is unlike included, does not actually declare anything. It merely makes things visible. So this might suggest that it doesn't really matter where we import things. And it is the case for implementation units. For interface units, there are two important differences. Only an import in the module Purview is visible in implementation units. And only an import in the module Purview can be re-exported. So the guideline here is to, in interface units, to always import, to import in the module Purview unless you have a good reason not to, and you understand the reason, so you're doing it consciously. And do it the same in the implementation units, just for consistency. So one less thing to think about. As an example, inclusion still out of Purview. In the Purview, we import our modules, include special headers. The rest is the same. So based on these 6 guidelines, we can actually come up with a typical module template. Right? We start with headers. We then start module Purview, where we import our modules. We include special headers, and comes the module interface. And at the bottom, we include inline and template files if you have those. The same for implementation template. Headers out of the module Purview again. Then we have start the module Purview. We add extra imports. Remember, we don't need to repeat the ones that were imported in the interface. And then we have the module implementation. Let's also briefly talk about module naming. Module names live in separate name, what I would call a name plane. They don't clash with namespace names, function names, type names. Standard also does not prescribe a hierarchical semantics for modules, though it's customary to call, so for example, hello core a submodule of hello, and to also expect that importing hello will also import recursively its submodules. So the guideline we use in our own project we came up with for naming modules is to start with a project or library namespace and finish with a name that describes the functionality of the module. Oftentimes we found that a module is dedicated to housing a single or primary entity, for example, a class. So we just use that name directly. Worked very well. So here's a concrete example. That's the utility library I mentioned earlier that, well, I showed you how it was built modularized. So it's called libbutl. Everything in this library lives in the butl namespace. And as you can see, all the modules start with a butl name, and then most of them are just names of the main entity that they are dedicated to. Okay, when do we re-export our modules? Look at this example. So we have a function that uses std_string in our interface, so we need to import std_core. Should we re-export it? Should we make it easier for our users so that they don't need to do it themselves? Well, I think most of you know that I'm opening a big can of worms here, and we are not going to be talking about it today, but I'll give a link at the end of the talk where you can read some thoughts on this subject. Okay, let's now see how we can modularize existing code bases. So this is where it gets interesting. At the outset, I would suggest that you start with a build system with proper module support. Your life is going to be, for any non-trivial code base, your life is going to be hard enough to also fight this battle. Another point is it helps a lot if you have a well-modularized, in a general sense, set of headers. Specifically, having header inclusions will really hurt because module interfaces cannot have dependency cycles. Also, if you're planning to provide a dual header module interface, then it helps to have a one-on-one mapping. So you have one header, one module. So I would actually suggest that you spend some time before attempting any modularization, trying to clean up and rearrange your headers. So we found that it helps quite a bit, though our headers are mostly pretty well separated. All right, let's start with understanding why modularizing this way is a bad idea. Well, imagine that our hello header belongs to our library, right? So we want to modularize it. Imagine it includes std_string, right? So we've already discussed why including std_string in the module preview is a bad idea. Here we're not only doing that, we are also exporting std_string from our module. So I think hopefully everyone understands this is not a good way to go. But what if this is the only way available to you? What if you want to modularize non-intrusively a library that you cannot modify? For example, standard library. Right? That build I showed you, it uses GCC standard library that is modularized, what we would call a Guerrilla Modularization approach. So you can work around this include issue. There are other issues, by the way. You know, for example, if your header declares a name with a local linkage, internal linkage, then this is illegal to export from an interface. But the biggest issue we found is actually including headers that you don't want to export. And you can work around that, if you really have to, by pre-including them out of the module purview. So here we pre-include std_string with the assumption that the second inclusion inside the header is actually going to be ignored. Needless to say, this is very brittle. I don't recommend it except for some prototyping or kind of exploratory modularization. But sometimes you have to do what you have to do. Okay, when it comes to modularizing our own code or modularizing things properly, we're actually able to change things. The biggest issue is the biggest constraint, or biggest limiting factor is the fact that implementations currently do not support mixing and inclusion, inclusion, and importation of the same entities in the same translation unit. So you cannot, for example, include IO stream and import std.io. And I don't think it's actually an unreasonable limitation. I mean, this thing is already complex enough to support some crazy scenarios like that. So this bites especially badly when you try to switch to a modularized standard library. And the reason for that is it's used everywhere, presumably in your code. The two strategies that we found works best if you plan to switch to modularized standard library exclusively, so you are getting rid of headers and replacing them with the imports, then it may make sense to do that first before even modularizing any of your own code. So you switch, you make sure everything builds and works, and then you continue with modularizing your own code base. And if you can afford that, if you can make it work, I would strongly recommend going this way. The alternative strategy is kind of an inverse. First, modularize your whole code base while continuing using standard library as headers, and then switch at the end. Now, the reason to wait until you modularize your entire code base is to get rid of includes. Right? If we continue using includes for some of our modules and we're modularizing some others, and we are switching to the standard library in the process, you will end up, well, we ended up with situations like that. Hello core is still a header, so we include it, but it happens to include IO stream, but we are already switching to modularized standard library. This just blows. I mean, this doesn't work. When it comes to modularizing our own components, the strategy that we found works best is to identify and modularize interdependent sets of headers, one set at a time, and starting from the lowest level components, so that any newly modularized set only depends on the previously modularized one. Right? Now, it would be nice to be able to modularize one header, one module at a time. Again, this does not work very well because of if you are still using includes. Sometimes you'll end up with bizarre situations like you include a header that imports a module in its own implementation unit. So none of the implementations currently handle this gracefully. Okay, let's quickly talk about providing backwards compatibility. We've identified 3 levels. So modules only, you don't provide any, you just switch to modules. Lucky you if you can do that. Modules are headers, where we support headers for backwards compatibility, but we expect our library and its consumers to be on the same page. They both using modules or both using headers. And finally, we have this 3rd level where we actually support cross-usage, right? We support consuming our library built as modules as headers, and even the other way around. Now, that might seem far-fetched to some of you, but actually fairly plausible case. Right? If you have a ton of existing consumers and none of them can be, and they cannot be all switched to modules at the same time, or ever, in fact. All right, modules only, pretty simple, follow the templates and guidelines above. I would also strongly suggest that you consider using modularized standard library exclusively. Using standard library as headers in a modularized application is actually more painful than using it in a header-based application. If you want to know why, I'll give a link at the end. Modules are headers. So here we expect the consumers to be adjusted to be kind of on the same page as us. The way we found this can be set up, I mean, there are probably thousands of ways you can arrange this and set it up, but what worked for us is to reuse the interface file as a header when modules are not available, and to decide which mode we are in, we use the feature test macros. So the CPP modules is defined if we have modules available, And cpplib modules is defined when we have also modularized library. See what it looks like. Remember I talked about getting rid of the preprocessor. Doesn't go this way. But yeah, the idea is that you will probably get rid of it once you switch to exclusively to modules. So the first thing we do is we make sure that, so this is the interface unit, and we need to craft it in such a way that it can also be used as a header. So the first thing we need to make sure is that it's not re-included in the header mode. You can probably make it work with include guards. It will just get really ugly, I think. And I think it's just better to bite the bullet and use pragma once. Then we have the C includes, for example. Then we have a block of includes for when standard library is not modularized. And we have some other includes that you might have. Then we have a block for when we are actually in a modules mode. So we start the module Purview. And then we have a block of imports for the modularized standard library. Now, you can probably arrange it a bit differently, probably shorter. The thing that we like about this approach is that it's linear. It doesn't have too many else blocks, too much nesting. It also will be fairly easy to clean up once we drop support for headers. Just basically remove blocks or remove if divs. Corresponding module implementation unit. So instead of pragma, once we have an include for when we are in the header mode, then we have the, again, C includes, a block of includes for the standard library. Now, here we have to actually re-include the standard library headers we specified in the interface. And this is where that pain of using standard library as headers in a modularized library comes. You can read why we have to do that. It's actually fairly annoying. So then we have other includes. We have the start the module Purview, and again we have extra includes extra imports for the standard library. Now this more or less follows the template that I gave earlier, just kind of is a little bit uglified to also support headers. So the adjustments to consume are straightforward. We import if modules are available. We include the interface unit as a header if they are not. The last level is fairly, you would imagine this thing gets really ugly, and there's a bit more preprocessor involved, but we can actually tweak the previous model to work without too many changes. The only thing we'll have to do, we'll have to keep the old header name, so we'll have kind of 2 files now for each header module pair. I'm not going to show the code, so I'll give you a link where you can read about it. But yeah, it's slight complication over the previous model. And with this, I think I'm pretty much done. So everything that I've covered in quite a bit more detail and discussing quite a bit more nuances, you can read about in the build system manual. There's a whole chapter on C++ module support with introduction. All these guidelines, all these templates are listed there. I also want to thank these individuals for answering my questions about modules and reviewing patches. And yeah, thank you. Any questions?
Hi. So I do actually have a question. At the beginning of your talk, you had a quote from Richard Smith saying that the compiler should not become a build system. Mm-hmm. And I had asked Gabby on Monday how, if you have module B and module A, and A imports from B, and you compile A first, what happens? So how do we, and his response was, we'll make the build systems understand modules. How do we do that without having the build system turn into a compiler?
Well, I can tell you how it's done in build 2. If you study the specification for modules, one nice property of the grammar rules is that all the module declarations are what I would call top level, right? They are all at the top level of your name scoping, right? The module declaration has to be in the global scope. So what we didn't build to, we just pre-tokenize shallowly a translation unit and extract all this information. Now, at first, even to me, that sounded a bit heavyweight, but in the end, it actually worked perfectly. The cost of that on the modern machines is like not even 1% of your build time. And in the end, as a bonus for doing this, we actually got a more precise change detection. We now hash the tokens that we get. So any white space change that you make to your translation unit, we can now ignore.
Okay, and so does that include, like, if someone were to, do the worst case of we're going to use the preprocessor to change like the module name or to, change like what imports there are?
Yeah, if you're doing that, then we have to run the preprocessor before that.
Okay.
Which again might sound like a crazy idea, but interestingly, on modern hardware, it's again like 1% of your build time.
Okay.
That was actually one interesting finding, surprising finding. Like, let's say, how many percentage points of your build it costs to pre-process all your translation units, right? You'll think maybe 5%, maybe 10%. Right? It's actually less than 1%.
Okay, thank you.
Hi, this is John Lakos from Bloomberg. I want to thank you for the talk. I'm trying to learn about modules. I was approached about 10 years ago. Somebody asked me my opinion, and I said, why do we need modules? Well, 10 years later, I think we do need modules. But I wanted to ask you a very practical question. I have a company that has over 5,000 developers. We have an immense amount of legacy code, unbelievably large. It includes Fortran, C, C++. We're moving forward. It turns out our core infrastructure, by some luck, is levelizable. I don't know why, but it is. And I was wondering, how would you advise that we take advantage of modules at Bloomberg? Because the chances that we're going to go back and retrofit code from the 80s to use modules is slim. And we want to start using them, but we have clients right now that are perfectly happy not to use them. And then later, we're going to have clients at the middle level who do and don't use them. And then we're going to have a client at the top level that says, I want to use the core infrastructure, and I have some middleware that uses modules and some middleware that doesn't use modules, both of which use BDLT date, which is at the bottom. And now what do I do? So how would you advise Bloomberg to adopt modules, given what I just said?
My follow-up question, can you switch all the consumers of, say, that date at the same time to modules, or do you have to maintain some as modules, some as
Okay, I don't know if there's a word that's stronger than no.
Okay.
But if there were, I would use it.
All right. Well, in this case, I would suggest you provide a dual. So you can take, if you start from the lowest level, right? You take the component that nobody else, that does not depend on anything else, right? And it's not necessarily a single header. It can be an interdependent bunch of headers. You modularize it.
What does that mean?
Provide.
What do you mean? Do I actually have to change the code, or can I make something that depends on it that has a module interface? Do I have to change the original source?
You can, if you can change the source, it will
I can't change the source.
Well, then I guess you can define a module interface. You'll just have to maintain the interface. Well, since you are not changing it, I'm presuming ever, right? So you cannot change it, so you never change it, right? So you can just copy an interface.
No, I can't copy it because it has to be the same type, because they're used by module users and non-module users. And I can't touch anything. No code at all can change.
Oh, well, you have a header, right? With some declarations. A header.
Yeah, I have a header, yes.
Yeah. So can you open it in an editor, copy, open another file with a different extension, paste it in there?
I can do that.
So you're not changing the header.
Right.
Header is read only.
Okay.
And then you put X, you basically have a bunch of includes maybe for C or C++ standard library, and then you have, I don't know, the namespace.
Are they the same C++ class, the same date class now? I have two different things. They're the same.
As long as you're exported, remember I mentioned that an exported name looks exactly the same as if you never used a module.
So to be very specific, I have the original date class, and now I have something else. I happen to use cut and paste to get there, but I have something else that depends on the original date class that exports it through a module interface. Is that correct?
Right.
I wouldn't really need to cut and paste it. I could just simply refer to it, right?
Well, that goes back to that Guerrilla Modularization technique that I described, right? Your problem will be that you will, if you just, export a header, wrap a header in the export group, you're gonna export, your C headers that you include there, your standard library headers. So you can hack around that by pre-including
But you can
them.
imagine the problem of duplicating the code. So I have two different full implementations of a class and keeping them in sync. That would be problematic, wouldn't it?
You said you never changed it, so why would it be?
Well, I'm allowed to refer to it. I'm not, by the way, this is not a joke. This is extremely important. And the reason is that we do have code that is stable for 30 years, and yet we want to be able to have new clients adopt modules. So we have to, there's a duality here, if you understand. It's like a dialectic, right? We got two truths. We got this truth and we got that truth, and they have to coexist. And the trouble is, you can't change the world in lockstep because you can't. And therefore, we need a strategy for modules that allows us to incrementally and additively make that change.
But
This is
I
hugely
believe
important.
there is. You have certain constraints, right? You cannot change the header.
By the way, it's not just me. A9, Microsoft, Google, Facebook all agree. Just saying.
Okay.
Hey, thanks for the talk. So you mentioned that it's a bad idea, and it makes sense that if we somehow include like string header inside the module purview, can we enforce that though? Because mistakes happen, right? And some developer did something and passed the code review for some reason. But will the compiler catch it? Will the build system catch it, or how does that work?
Okay, so let me see if I understand the question. Is there a way to enforce, maybe to mark a header as not, so that it cannot be included in the
Especially
in the
like
module
the standard headers, especially the standard
purview?
headers. Like, can we force that nobody includes standard headers in the module purview?
I haven't seen anything, but that might not be a bad idea, and it might not actually be that difficult to implement. A compiler could easily define a macro once it's in Purview.
Okay, so it's up to the compiler then, or?
I think it's a good suggestion, a good point, but we are also in quite a bit early stages of this whole thing. But yeah,
Okay, cool, thanks.
cool.
Hi. How do you think modules compare to precompiled headers in terms of build speed?
I personally haven't used precompiled headers too much because I believe it's just a hack. So to me, when people compare precompiled headers to modules, I don't think it's kind of apples to oranges comparison. So I don't know. Anyone knows what speed up you get if you use a Visual Studio precompiled header in a typical application? Is it 2 times, 3 times? I don't know. 10 times. Well, but I don't know how many of you are aware how it's implemented in Microsoft. In Microsoft, for example, in the Visual Studio compiler, I was told that a precompiled header is a compiler memory dump. So when you use a precompiled header, it just loads the memory. So I don't know. Can you compare something that is part of a language to a memory dump? Probably not.
Thank you. Hi, thanks for the talk. My question was about like the distribution mechanism for this. So you mentioned earlier that we don't want to use these to quote unquote install modules, but there's nothing stopping us from generating the implementation in a separate DLL or lib that is then linked into the final thing. So if we have, is it a good model to sort of have your actual module implementations compiled somewhere and then have separate interfaces that sort of allow you to bridge your code to this compiled lib that then you take everything together? Or is that a bad approach to solving this problem? Because we would love to be able to take our code and compartmentalize it where there are chunks of it that we just don't compile regularly because they're more or less stable unless we make changes in there. And it would be nice if we could use modules to sort of like bridge in between rather than having to include tons of headers and getting into just nested header hell. Is it a good idea to sort of build your module implementation separately, or is that a bad idea? Because you keep talking about the recompilation cost, and we're trying to figure out, is there a way to avoid having to recompile your module implementation for each file and each place that's reusing it?
I'm not certain I understand which problem you refer to. Are you trying to avoid recompiling the binary module interface, maybe
yes.
shipping? You can do it if you have a controlled environment. If you say all my projects are built with exactly the same options, there is no reason you cannot ship a pre-built BMI. In fact, you can even do that theoretically without this restriction. Just the build system needs to be able to detect, okay, this BMI I cannot reuse, so I have to build it. Or no, these are compatible, so I can reuse it.
Okay. All right, thanks.
Last question.
Let's say I want to put interface and implementation in one file, and then if I change only the implementation, does it mean that I have to recompile all the consumers will have to be recompiled? Is it a limitation of the build system, or does the BMI change as well if I only change implementation?
Good question. I suppose you can imagine an implementation that would keep the, if you haven't changed anything in the interface, it will produce identical BMI, which can then be, checksummed by the build system and detected that there are no changes. Again, very early days, but again, not a bad idea, I think, to consider.
Okay, that would be nice.
Thank you.